Ah, okay, thank you. Thank you. Good morning, all the students. Welcome to online GATE coaching classes in geotechnical engineering in the specialization of civil engineering. Up to the last class, we have seen several topics in soil mechanics. Last class, we have dealt the chapter consolidation of soils. Now, let us move to another chapter, shear strength of soils. Shear strength of soils. Here we are going to discuss first the general theory related to the shear strength of soils, various tests that are to be conducted, and the analysis of various tests, and more general information about cohesive soils and also non-cohesive soils with reference to the shear strength of the soils. Then some generalized numerical problems, and afterwards previous GATE questions. So this is the total lecture today. Now let us move to shear strength of soils. And every one of you know that shear strength is the resistance offered by the soil against the shear deformation. So here shear strength of the soils means it is going to be resisting shear resistance against the shear deformation of the soil. So already in the strength of materials, we have seen different types of strengths that are there for any structure. The same concept is being involved here also in case of shear strength of the soils. So it is the resistance against the shear deformation and resistance by means of the soil. Resistance by means of the soil means it can again consists of soil particles, air, and also the water. So depending upon the constituents present and percentage of constituent present in the soil, the shear strength parameters will vary. And for a given soil, shear parameters are not always constant. And shear parameters are cohesion and also angle of internal friction, C and phi values. These values are not constant for acting on the soil. So that we will see little later about how angle of internal friction varies with reference to the several things. And shear strength is the very important engineering property which controls the stability of soil mass under several loads. And normally this shear strength will be used for computing the bearing capacity of soil and analysis of stability of slopes in soils, and in retaining structures, computation of the earth pressure and also the total pressure acting on the retaining walls. Like that, several applications are there with reference to the shear strength of the soil. And normally shear strength will be derived from several means. The shear strength may be obtained by means of the interlocking of the particles or interlocking of the soil solids. Second one is frictional resistance between the individual soil grains. When some load is acting on the soil, then friction will develop between the soil particles. So that is called the generalized friction between the grains. Sometimes it may be sliding friction in which the particles are sliding, or sometimes we can call it as rolling friction and the particles are having friction while rolling from small disturbance, or some combination of these two. And another one is adhesion or cohesion between the soil particles. So in general, the strength of the Strength of the soil with reference to the shear is by means of number one, interlocking of the particles, two, frictional resistance, number three, cohesion or adhesion. So because of these three actions, shear strength of the soil induced. And here different types of soils are there. You can look at granular soils or sands. The frictional strength of the granular soils or sands may be from the first two. What are the first two? One is we can look at in the previous slide. In the previous slide, the various factors affecting are number one. You can look at the bottom. Number one is resistance to interlocking, and two, frictional resistance, three, adhesion. So normally what is going to happen is granular soils or sands have shear strength because of the interlocking of the particles and also the frictional resistance. So that means first two properties associated with the granular soils or sandy soils, whereas the cohesion or cohesive soils, the friction induced, the shear strength induced in the fine grained soils, particularly in clay soils, it is because of the frictional resistance and also adhesion. So that means for the sandy soils, first two parameters are dominating, and for the clay soils, second two parameters are dominating. And sometimes the clay may be very pure clay, perfect pure clay. In such a case, the entire shear strength depends on the cohesion only. Entire depends on the cohesion only. So again, I'll tell you one thing. For granular soils, first two parameters are important. For cohesive soils, the second two parameters, that is frictional resistance and cohesion, is important. And most cohesive soils, only the cohesive property will give the shear strength for the soil. And now you know what is cohesion. Cohesion is the property of the soil holding its properties together. So all small particles of the soil will hold, and that property is called the cohesion. Cohesion is an important property, particularly in the fine grained soils. Cohesive soils possesses actual cohesion. Example is clays. And you know another type of soil is cohesion less soil. Cohesion less means there is no cohesion in the soil. For example, sand. So the sand particles are not intact. So all the particles are individual. When you press the soil, cohesion less soil, it may be intact. When it releases naturally, all the particles are separated out. So that means there is no cohesion. There is no intact media for holding all the soil properties in case of cohesion less soils. And another parameter is structural resistance. This structural resistance normally is the structural arrangement of soil particles, and normally it affects the shear stress. Already I told you the soil may exhibit different types of properties, though soil is the same. So it will exhibit different shear strength parameters at different void ratio and different rate of loading. So that means for a given soil, already you have seen several properties are same for a given soil. For a given soil, in the last class we have seen coefficient of consolidation, CV is the same. And for a given soil, several other properties are same. But in the case of shear strength, the cohesion and also angle of internal friction varies with the variation of the void ratio and also the application of the load, rate of loading. So that means the properties are always depends on the variation of the parameters. Now let us see the friction. Friction means the internal friction between the particles resisting the shearing friction of the soil mass. So normally the friction may be either sliding friction or it may be rolling friction or a combination of the two. So because of this friction, frictional resistance will develop between the soil particles. Angle of internal friction, we call it as phi. Angle of internal friction is a measure of resistance of the soil to sliding along the plane. Angle of internal friction is the friction angle which measures the resistance of soil sliding along a plane. So this angle of internal friction phi depends on the several factors, and the major factors are shape of the particles, surface roughness, type of interlocking, lateral pressure, and etc. Several other properties, minor properties also there, that will be discussed at the end of the chapter. How phi value varies with even numerical value of the phi varies with reference to the various change of parameters. Then another parameter is angle of repose. Angle of repose is the angle at which the heap of the soil forms. You can look at here, it is a heap of the soil, and when you keep the heap of the soil, there it possesses some angle. It possesses some angle. That angle with reference to horizontal is called the angle of repose. So angle of repose and angle of internal friction both are not the same for all the soils. Both are different, but for a loose sand, for the loose sand, both angle of repose and angle of internal friction are approximately the same. So angle of repose is the angle made by the heap of the soil with reference to the horizontal, whereas angle of internal friction is the angle 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 to measure the resistance of the soil along a sliding plane. So these are the basic differences between angle of internal friction and also angle of repose of the soil. And initially, more developed theory which is called Moore theory, or we can call it as Moore failure theory. Moore theory, or can call it as Moore failure theory. So initially Moore has given some failure envelope, and it follows S is equal to sigma F multiplied by tan phi. Sigma phi is normal failure stress. S is the shear strength. S is shear strength, normal failure stress, and tan phi is the angle of internal friction. So it follows the straight line or approximately curve regarding these two parameters. And then Coulomb extended the Moore's theory, and sometimes we can call it as Moore-Coulomb theory. So according to Coulomb, the shear strength of soil consists both cohesion and also the friction angle. So you can look at here, S is equal to C plus sigma into tan phi. So in Moore's theory, it is considered only normal stress and cohesion is completely neglected. But Coulomb extended the Moore's theory and suggested a formula, an equation for the shear strength of the soil, S equal to C plus sigma tan phi. And S is the shear stress at the failure, sigma normal stress, C cohesion, phi angle of internal friction. And later, of course, C and phi are called the shear strength parameters, that you know. C and phi are not constant for a given soil. If the soil is given, the size of the particles and other parameters may be same, but C and phi are not constant. It depends on the drainage conditions and also the type of test conducted. Drainage conditions means whether the drainage is permitted, water is permitted through the soil for consolidation or not, and similarly the type of tests, whether what type of forces that are acting on the soil, etc. And you can look at these diagrams. You can look at these diagrams in the previous Moore Coulomb theory. Previous Moore Coulomb theory, S is equal to C plus sigma tan phi. S is equal to C plus sigma tan phi, which is generalized equation that can be used for any type of soils. So this equation can be represented in the form of a graph. In the first case, you can look at S is equal to C plus sigma tan phi, or we can, in place of S shear strength, we can call tau is the shear strength, and this is the Coulomb envelope, Coulomb failure plane. Envelope means failure plane. So shear stress is equal to C plus sigma tan phi. And here the ordinate of the y-axis is called the C, and the angle of the failure plane with reference to the horizontal is the angle of internal friction phi. So this is how the Coulomb represented, and it is also an equation not passing through the horizon, but it cuts the y-axis at ordinate of C, So that y-intercept is called the cohesion, and the angle of the failure plane with reference to the horizontal is the angle of internal friction. And sometimes if the cohesion is zero, you can look at below this. It is particularly for Coulomb envelope for C5 soil. C5 soil means the soil containing both the properties of cohesion and also angle of internal friction. And in some specific case where C is equal to 0. When C is equal to 0 means that is cohesion less soil. When there is no C, it is cohesion less. For cohesion less soil, tau is equal to sigma tan phi. You can look at the next one where y-intercept is C equal to 0, and it follows with the horizon. It is passing through the horizon. So the shape of the envelope is again straight line, and which is given by the equation tau equal to sigma tan phi, where phi is the angle with reference to the horizontal. And this is particularly pure sand. Pure sand means it is cohesion less, no cohesion. So that means this case is valid for C is equal to 0 or only phi exist. Phi exist means cohesion less soils. In another case, sometimes the soil may not be having phi value. Soil may not be having phi value. So in such a case, tan phi is equal to tan phi means tan 0 equal to 0. So the second term vanishes and tau is equal to C. So in such tau is equal to C, phi is equal to 0. So when phi is equal to 0, angle of internal friction is 0. It is the case of pure clay. It's the case of pure clay, and the failure envelope is horizontal in nature. Failure envelope is horizontal, and equation of the line is tau is equal to C. So in general there are three different types of soils. One is pure clay, envelope is horizontal and with the y-intercept of C, and pure cohesive soil, cohesion less soil, pure sand. Then for this failure envelope is passing through the horizon. Another one is generalized soil which contains C and also phi, which is having y-intercept of C and also angle of internal friction phi. So these are the three generalized failure envelopes, and these envelopes are useful in evaluation of the various properties from the tests. Then afterwards, Terjagi has given some other concept. Terjagi has given some concept which is completely basing on the effective stress principle. So in all previous discussion, in the entire previous discussion, whatever the value of phi, whatever the value of sigma, whatever the value of C, all these parameters with reference to the total stress, and it is not considering the pore water pressure. So, but Tarjagi has given a concept. The principle is completely basing on the effective principle, effective stress principle. So, wherever the stresses are there, the stresses must be effective stresses only, and total stresses are not to be considered in the analysis. So in the Moore Coulomb, already the equation represented by C and phi, these are the two parameters which are basing on the total stress conditions. Whereas Tartaggi established the normal stresses which control the shear stress of soil are the effective stresses. Effective stresses are not the total stresses. So that means the same equation again modified S is equal to C dash plus sigma dash tan phi, where C dash is the effective coefficient, sigma dash will be the effective stress, and phi will be effective angle of shearing resistance. Actually it is phi dash. Phi dash will be the effective angle of shearing resistance. And already you know how to calculate sigma dash in earlier chapter. Sigma dash will be equal to total stress minus pore water pressure. Total stress minus pore water pressure. So by substituting all these effective parameters, you will get the effective shear strength of the soil, and this theory was proposed by Tarjagi. So there are three theories. One is Moore theory, then Moore-Coulomb theory, and the extension of that will be Tarjagi's effective stress principle concept. And now coming to the different types of tests based on the drainage conditions. Different types of tests based on the drainage conditions. So normally already we have seen for a given soil C and phi are not constants. It varies with the type of drainage conditions. Whether drainage is permitted while testing, whether drainage is not permitted, or whether the soil is in a dry state of testing, or whether the soil is in saturated condition of testing. So these are the various parameters to be considered for evaluating the shear strength parameters. And here several tests are there. You can call first one unconsolidated undrained test. So that means unconsolidated means no consolidation, and undrained means no draining, no draining. So here these are the two different words that we can look at. Consolidation, last class we have seen consolidation takes place in the soil means expulsion of pore water. Expulsion of pore water from the soil, we can obtain the consolidation of the soil. So that means unconsolidated means there is no water, there is no drainage, there is no drainage while applying the axial load or while applying the normal stress. So normally for the consolidation purpose, what type of force that we apply? It is only normal stress. When unconsolidated means the soil is in a dry condition, and while applying the normal stress. And another one is undrained. Undrained means no drainage while it is in the shear stage. There are two different types of forces that are acting on the soil for testing. One is normal stress, another one is shear stress. Because here in this particular chapter we are going to find out the shear parameters. Shear parameters. Even in principal stresses, you know, major principal stress and minor principal stress will be sigma 1 plus sigma 1 or sigma 2 is sigma x plus sigma y by 2 plus half into root of sigma x minus sigma y whole square plus 4 tau square. So that means the final stress or major principal stress or minor principal stress can be obtained by considering the application of the load both in the normal direction and also in the shear direction. Shear direction means horizontal direction, lateral direction. So here in consolidated means when the soil is to be consolidated means we are going to apply the normal stress. Normal stress is to be applied for consolidating soil. And when the drainage is permitted means that is in the shear stage, whether it is drained or undrained. So in this particular case, unconsolidated means no drainage is permitted during axial load, axial stress. And undrained means no drainage is permitted in the shear stage. So in total, while during the entire test, there is no drainage. Drainage is not permitted both in consolidation stage and also in the shear stage. This is most important point for differentiating these two. Since there is no drainage, so no dissipation of pore pressure during the test. When there is no dissipation of the pore pressure, the test can be conducted time 5 to 10 minutes. And it is undrained tests, particularly for low permeable clays. Low permeable clays, this type of tests can be conducted. And normally this type of tests are used for short-term stability analysis, foundations, excavations, and also earth dams. We can conduct unconsolidated and undrained test. So this test is can be conducted very quickly. U and undrained test, so that U test. And since it is quick test, we can call it as Q test. So consolidated undrained test. While consolidation of the soil takes place means drainage is permitted. Consolidation process means removal of the water from the soil is the consolidation process. So during the consolidation process, drainage is permitted, whereas during the application of the shear stage, no drainage is permitted. No drainage is permitted. So here you can look at drainage is permitted until consolidation is completed. And no drainage is permitted during shear lag. So in the second stage, where the horizontal stress is applied, there is no drainage. Drainage is not permitted. In such a case, it is called CU test. Consolidated C, U means undrained test. And we can call it as R test. Why it is called R test means Q is the quick test and another test is S test, slow test. And in between alphabet Q and S, alphabet R, so that's why it is called R test. And in this particular case, because consolidation takes place, volume change will takes place during consolidation. But during shear stage, volume change do not takes place. And this particular type of testing is to be used for sudden drawdown cases. Another type of arrangement is consolidated drained test. So that means consolidated during the consolidation, we are going to permit drainage from the soil. Consolidated means we are permitting the drainage during the normal stress, during the application of the normal stress. And it is also drained test. We are going to permit the drainage during the shear test also. That means throughout the test, throughout the conduct of this test, drainage is permitted. Drainage is permitted throughout the test during the application of both normal stresses and also shear stresses, so that full consolidation occurs in the process of CD test. And it is a very slow test. Normally it will take 2 to 5 days. Once the consolidated and drained test is set up, and it will take minimum of 24 hours and in general 2 to 5 days. So that's why it is called slow test or otherwise S test, and consolidated drain means C and D. Consolidated C, drained D, CD test. And in this particular stage, the drainage is permitted, so naturally volume change will take place to the large extent. And during the entire process, water is allowed, drainage is permitted, and these parameters are now Cu and also phi u, because Cu and phi u. Well, since the drainage is permitted, all the parameters will be considered as the effective parameters, that is C dashed and phi dashed. Because here pore water and pore water pressure etc. will be there, and effective stresses or effective parameters are to be considered, C dash and also phi dash. And in general for undrained test, undrained means where there is no drainage during the shear lag, shear application. In such case we can write Cu phi u. So when there is no drainage, it is undrained, Cu undrained, phi u undrained. It is these are the two different parameters, two different symbols that we normally use for the undrained test. So look at, there are three different tests. Number one is UU test, unconsolidated undrained test. Number two, consolidated undrained test, CU test. And third one is consolidated drained test, CD test. So these are the three different types of tests that can be used in various testing equipment while conducting the experiments. And several shear strength tests are there in the laboratory and also in the field. One is direct shear test, triaxial compression test, unconfined compression test, laboratory vane shear test, torsion test, ring shear test. These are the various tests to be conducted in the laboratory. And field tests also, one is vane shear test. Vane shear test can be conducted both in the laboratory and also in the field. So in the laboratory, the equipment is small, which is suitable for conducting the experiment in the lab. Whereas in the field, the size of the equipment is big enough, and that can be used directly for conducting the tests in the field. And one more is penetration test. So these are the various tests for finding the shear parameters. Now look at one by one the direct shear test. So here our concentration is more on the basic principle in each and every test, and also the analysis. We are not going to concentrate much on the how test is conducted in the laboratory, etc. is not of that much important. We are not focused on the overall procedure of the conducting the various tests. So in the case of direct shear test, as the name implies, that the shear applied directly on the soil specimen. Shear directly applied on the soil specimen, so that's why it is called the direct shear test. And normally the size of the soil specimen is 60 by 60 by 20 millimeter test, and generally it will be conducted on cohesion-less soil. Cohesion-less soil means sandy soils. This test is most appropriate for cohesion-less soils. Cohesion-less soils. But in the experiment, we can use all the three types of drainage conditions: UU, UD, and CD. But here there is no particular measurement in majority of the equipment, and the testing is to be conducted only on undrained, unconsolidated mode only, UU only, and it is most useful for granular soils. So here granular soils means normally cohesion value is 0. cohesion value is 0. And sometimes it can also be used for C5 soils also, both cohesion and also angle of internal friction present. So what is going to happen here? We are going to apply a horizontal normal force and also the shear force directly. The shear force will be applied exactly at the failure plane. And that failure plane is always predominant. You can look at here, the sigma n is the normal stress that it is subjected, and horizontal shear stress will be acting, and the specimen will break, and finally the principal stresses corresponding to the principal stresses of the soil sample are sigma 1 and sigma 3. So sigma 1 is a major principal stress. This sigma 1 is because of the normal stress and also shear stress that is acting on the soil, and finally the stress at a particular point in the soil mass is represented by the stress diagram sigma 1 and also sigma 3. So in this particular case, what we do in the laboratory is we are going to apply one normal stress, and find out the failure shear stress. And second normal stress, corresponding failure shear stress. Then third normal stress, corresponding failure shear stress. So when you know 3 points or more than three, what you do is between a curve is plotted. The curve is to be plotted between a normal stress on the y-axis and shear stress on the shear stress on the y-axis and normal stress on the x-axis. You will get some points here, say point 1, point 2, point 3. And if you join this, you will get the straight line. You will get the straight line. If the straight line is if the straight line is intercepting at y-axis, the ordinate is called the cohesion. Ordinate is called cohesion, and corresponding angle with respect to horizontal is called the phi. So in the laboratory experiment, you will get a combination of the sigma normal and shear stresses, 3 or 4 values accordingly, 0.1, 0.2, 0.3, 0.4, etc. And passing through those points, it will be a straight line. And it intercepts at y-axis. The ordinate of the y-intercept is called the cohesion, and horizontal angle is called the angle of internal friction. And you can look at the stress diagram. This is called the major principal plane, and this line is minor principal plane. And we can also construct the Mohr circle with sigma 1 left side and sigma 3 on the left side, minor principal stress, sigma 1 on the right side of this particular curve. And it has its own merits and also demerits. Let us not spend much time. It's a very relatively simple test, and it is suitable for conducting all types of soils, both cohesive also and also cohesionless soils. But it will give most accurate value. For the cohesionless soils. And demerits. What is going to happen is there is no control of drainage here, and exact value may not be obtained, particularly for the soils having cohesion. And measurement of pore pressure is not possible in this case. And the failure plane is always horizontal, which is fixed. And sometimes the soil may have failure plane some other, but because of the predetermined plane and the forces applied exactly at the horizontal, failure plane is always horizontal. So these are because of these demerits, the value that is obtained from the direct shear stress test is more appropriate and not exact in all the directions for all types of soils. But for cohesionless soils, it will give exact value of the shear parameters. Then triaxial compression test. Triaxial compression test. So here triaxial compression. Compression is applied. Compression is applied to the soil in triaxial. Triaxial. That means stress is applied vertical direction, x direction, z direction. All the three, x direction, y direction, and also z direction, we are going to apply the stresses. So that's why it is called triaxial compression test. So normally the specimen is of cylindrical shape, and height of the specimen is normally twice its diameter. And application of the stress is in three-dimensional. Stress applied x direction, y direction, and also z direction. So here, in the case of axial direction, we apply normal stress. The axial direction means the force along the length of the specimen. Force along the stress along the specimen is called the axial stress, which is vertical. And whereas in other two directions, two lateral directions, those stresses are called the minor stress and also intermediate principal stress, which normally we call it as cell pressure, which we call it as cell pressure. And we can look at this is the test setup arrangement. Test setup arrangement. What is going to happen here is this is called the perfect cylinder. You can look at here perfect cylinder. So initial vertical lines, it is a perfect cylindrical in shape and perfect cylinder. So that means we can see what is going to happen inside and how the pressure is applied through the water, etc. So that means this perfect cylinder is provided on outer periphery of the soil specimen. It is called the soil specimen, and because of the pore water in the perfect cylinder, the lateral forces will be applied. This is called the cell pressure. This cell pressure is uniform in around the periphery of the soil specimen. This cell pressure is uniform around the periphery of the soil specimen. That means in both x direction and also z direction, the stress is equal to cell pressure. And another stress that is acting on to the soil is direct stress or normal stress. Normal stress is acting through the loading piston, which is in the vertical direction. And you can look at the various test setup arrangement for the triaxial apparatus. You can look at it is a soil sample, and this soil sample is covered by membrane, so that the water in the perfect cylinder may not directly in contact with the soil sample. And this is loading cap, and over that loading piston and load will be applied appropriate to the soil. And this is overall guiding arrangement. And at the top of the soil, yellow color is there. It is protective membrane. Yellow color is there. These are the these two we can call it as porous plates. Top porous plate and also bottom porous plate. Porous plates are provided because to allow the drainage. So from the soil, if any excess water present, and because of the pore water pressure, the water will move through the pipe. So this is called the pore pressure measurement and also drainage. So here valve exists, and also meter will be provided. From this meter we can find out how much is the pore pressure in the pore water of the soil sample. And similarly, the water provided in the perfect cylinder with some pressure. with some pressure, because cell pressure is applied around the soil sample is by means of the cell pressure. So for that there is a drainage pipe and it is connected with the valve and also the meter arrangement, so that we can find out the cell pressure measurement, and whenever it is to be released, the valve release the valve, and so that water will move away and entire pressure will be released. So this is the overall setup, test setup. The cylindrical specimen is subjected to normal stress in the direction of the length of the specimen, and also the cell pressure in the lateral direction, and accordingly that entire test procedure is to be carried out. Now let us see the analysis, how it is going to act. So in the analysis, what is going to happen is, originally the length of the soil specimen is L. Originally the length of the soil specimen is L. And because of the application of the normal load, the soil gets compressed to delta L. Soil gets compressed to delta L. At the same time, at the time of failure, the cross-sectional area of the soil sample is AF. So the cross-sectional area of the soil sample is AF, area at the time of failure. Area at the time of failure. And A1 is initial cross-sectional area of the soil specimen. And you can look at here in the analysis, sigma C cell pressure, that will be called as sigma 3. That is minor principal principal stress is sigma 3, that is called the cell pressure, or otherwise confining pressure. And sigma D is called the deviator stress. Deviator stress means sigma 1 minus sigma 3. Sigma 1 is major principal stress, sigma 3 is the minor principal stress. And deviator stress means additional load divided by area at failure. Additional load divided by area at failure. So what is going to happen in the soil specimen? We are applying cell pressure to the soil, and then we apply normal load, and it is going to fail at a certain level. At that time, area of the soil specimen is AF. So what is going to happen? Additional load, whatever the additional load that is applied by means of the axial direction divided by area of the failure, P by AF, is called the deviator stress. Deviator stress. And knowing sigma 1, you can find out any of the three parameters, sigma D, sigma 1 and also sigma 3. But here, area of failure is more important. Area of at failure, AF, which is V1 plus delta V divided by L1 minus delta L. So use this formula for computing the area of the soil specimen at the failure. So that means initial volume plus additional volume. Why additional volume? Since the force is acting, then soil gets dispersed. Soil particles gets dispersed. So there is some increase in volume. And the length always decreases. Length always decreases. So it is L1 minus delta L. So you can look at V1, initial volume of the specimen, L1 initial length of the specimen, delta V change in volume of specimen, delta L change in length of the specimen, that's all. So for that you can find out AF. And sometimes for undrained test, delta V 0. Undrained means there is no drainage. When there is no drainage, there is no change in volume. There is no change in volume. So in such a case, the same volume of the soil will exist even at the failure also. Now look at this diagram. What normally we do is, we are going to apply sigma 3 initially for the a test setup, sigma 3. Here this is the value. And we apply the normal load continuously, normal stress continuously, and this is the major principal stress. point the soil is not going to fail. And again continuously we are going to apply the load for additional stress. Again if you plot the Mohr circle, this is sigma 1 2, and at this stage also it is not failed. That means this is second reading, and you will get one more reading, third reading. Here also it is not failed, and another reading. Like that several readings you can take, and at a particular stage it is going to fail. That is called sigma 1 f. So that means sigma 1 f means first sample has cell pressure of sigma 3, and its major stress will be equal to sigma 1. So the to the time of failure, what is the stress? That is important. So for the outer principal Mohr circle diagram, draw the tangent, and it will intercept the y-axis at a point at a height of c. That c is called the cohesion, and angle of internal friction is the horizontal angle. Or otherwise, you can consider only this diagram, this Mohr circle at the time of failure. Draw that one. For sigma 3 is called the cell pressure. Sigma 3 is called the cell pressure. And up to B, it is called sigma 1. Major principal stress is sigma 1. Sigma 3 is the minor principal stress. And with the center C as the circle, draw the semicircle. Draw the semicircle above the line. And once you draw it, then at any point, say D, if you plot a line, if you draw the tangent, that makes an angle of phi and also theta. And already you know the entire knowledge regarding the principal stresses. The radius of the Mohr circle is the difference of the principal stress by 2. Or otherwise, from the center O to C, what is the O to C? O to C is nothing but sigma 1 plus sigma 3 by 2. And similarly, the radius CB is nothing but the radius of the Mohr circle. CB is nothing but the radius of the Mohr circle, which is equal to sigma 1 plus sigma 3 by 2. Sigma 1 plus sigma 3 by 2. So these are the various parameters in terms of sigma 1 and also sigma 3. So what you do in this particular problem, it is very important to understand how to calculate the failure area. Once the failure area is known, you can find out sigma D. Sigma D is equal to P divided by AF. Once P by AF sigma D is known, already sigma 3 you can find out the sigma 1 value. So knowing the principal stresses, you can find out the shear parameters using the Mohr circle diagrams. And of course here, this is the generalized Mohr circle for C5 soil. When C5 soil is tested in triaxial test, you will get the envelope in this fashion. Whereas, so if the soil is considered only purely cohesive soil, the failure plane is always horizontal in nature. And if the soil is taken only sandy soils, then the failure plane is passing through the origin. And all these parameters, same for all the types of failure planes. It is minor principal stress sigma 3, major principal here is sigma 1, and all other things are same. Particularly in this diagram, not in this, any of the diagrams, if you look at this particular triangle, what is opposite side? Phi. Phi is the angle of internal friction. Angle of internal friction tan phi or otherwise sin phi. Say for example sin phi. Sin phi is equal to opposite side. What is opposite side? It is exactly equal to the radius of Mohr circle. Opposite side. Opposite side sin phi means you can look at sin phi is opposite side by hypotenuse. Opposite side is radius of Mohr circle, which is sigma 1 minus sigma 3 by 2. And in this triangle, what is the hypotenuse? Hypotenuse is this horizontal distance OC. Horizontal distance OC. What is horizontal distance OC? Sigma 1 plus sigma 3 by 2. So that you can use sigma 1 plus sigma 3 by 2 and ultimately sigma 1 minus sigma 3 by sigma 1 plus sigma 3. So this formula sometimes can be used for computing the phi value. That means if all the principal stresses known, major principal stress and minor principal stress are known, you can find out the angle of internal friction. And there are certain merits and also demerits for this. And at the time of plastic equilibrium, particularly in case of clay soils, and also combination of C5 soils, a combination of both properties C5 soils, we can establish the relation sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha. So this equation can be established at the time of plastic equilibrium of the soil. So it is related with the failure angle. Alpha means angle of the failure plane and C cohesion. Sigma 1 and sigma 3 are the major and minor principal stresses. So sometimes we can also write tan square alpha is nothing but n phi. We can put the parameter n phi. N phi is equal to tan square phi, so that you can write sigma 1 is sigma 3 n phi plus 2c root of n phi. So in this alpha is the angle of the failure plane, which is equal to 45 plus 5 by 2. 45 plus 5 by 2. So in this case, phi equal to angle of internal friction. So that means the failure plane is always at an angle of 45 plus 5 divided by 2. So just remember the plastic equilibrium equation sigma 1 equals sigma 3 tan square alpha plus 2c tan alpha, where alpha equal to 45 plus 5 by 2. And sometimes even in the case of previous triaxial test, what we do is we can conduct the several experiments on the triaxial test. What we do is apply cell pressure of sigma C1. So apply cell pressure of sigma C1 and it is going to fail at this stress. It is going to fail at this major principal stress. So it is sigma cell pressure. It is called the major principal stress corresponding to sigma C1. So draw the Mohr circle. And similarly, the next experiment for another soil sample, consider the cell pressure, another cell pressure. So for example, first 50, then 100, then 150, like that. By considering another cell pressure, the failure stress corresponding to the major failure stress and corresponding major principal stress sigma 1 is here. Draw the Mohr circle. And again take another sample with another magnitude of the cell pressure. It will fail at this point and draw the 3 more circles. Once 3 more circles are drawn, draw a line which passes through which touches all the semicircles. That means this line must be tangent to all the curves, and that is called the failure plane. This line must be tangent to all the envelopes. This failure plane must be tangent to all the 3 more circles. And this red line is called the failure plane. This failure plane intercepts y-axis at a height of cohesion C and making an angle of phi with respect to horizontal. So this is most appropriate, and that means in the triaxial test we are going to conduct three different specimens at three different cell pressures. And for three different cell pressures, the associated major principal stresses are sigma 1, sigma 2 and sigma 3. Accordingly, draw the Mohr circles. And observe the line which must pass through, which must be tangent to all the three Mohr circles, and that line is called the failure plane. That failure plane intercept y-axis at height of C, and horizontal angle with respect to horizontal is phi. So these are the two parameters from the point of view of the triaxial test. Or otherwise, we can also use modified failure envelope in this diagram. On y-axis sigma 1 minus sigma 3 by 2, and on x-axis sigma 1 plus sigma 3 by 2. If you draw the plot, and you will get some modified failure method, and that is not of that much important. And in case of triaxial test, there are three different types of failure of the soil specimen. If the failure original height is up to here and it is going to fail by means of little compression, very small deformation. When the soil gets small deformation before failure, the type of material is failure is called the brittle failure. And this brittle failure will occur in case of granular soil. In case of granular soil. And this is what is going to happen is the deformation is considerable. The deformation is considerable, but the shape still retains. The shape of the specimen still retains. It is called the semi-plastic state, and this type of failure will occur in C5 soils. Whereas another one is plastic failure. So before failure, large deformation takes place. Considerable deformation takes place before failure, then that failure is called the plastic failure. So these are the three different failures associated to the soil sample. So brittle failure is having well-defined shear plane. Semi-plastic failure you have shear cones and lateral bulging. You can observe the lateral bulging. And plastic failure, lateral bulging, expressed lateral bulging. So these are the three different forms of failure of the specimen used in the triaxial test. Next test is unconfined compression test. Unconfined compression test. So in the previous triaxial test, the major part there is confined test, because the confinement is provided by means of applying the cell pressure. So by means of applying cell pressure in all the x and also z directions, in all the lateral directions. But here in this particular experiment, compression test unconfined, that means no confinement. No confinement means no lateral pressure. No lateral pressure applied onto the soil. So that's why here the load applied is only axial load. There is no confinement. So that's why it is a special case of triaxial test in which confining pressure 0. That means there is no cell pressure here in both the directions. Only axial load is applied. Accordingly, axial stress is acting on the soil mass. And the test can be conducted only on the undisturbed soil or sometimes remolded cohesive soil, which can withstand without confinement. And it normally called as quick test or undrained test. Undrained means there is no drainage. There is no water involvement here. Here what is going to happen is the soil sample tested directly by applying the axial force in the direction of the axial direction. And here minor principal stress sigma 3 is always 0 because there is no lateral stress. And major principal stress is Sigma 1 is equal to load divided by area at the time of failure. And area at the time of failure is A1 divided by 1 minus E. 1 minus E. So here what is going to happen is there is no pore water coming out from the soil. There is no pore water coming out from the soil. Since it is undrained test, whatever the area at the beginning, whatever the area beginning or whatever the volume at the beginning, not the area, whatever the volume at the beginning, the same volume will present at the time of failure also. So that's why AF equal to A1 by 1 minus strain. 1 minus strain. A1 by 1 minus delta L by N. So in the previous case, triaxial test, you have seen the equation differently. What is that equation? The equation earlier used will be AF will be equal to V1 plus delta V divided by L minus delta L. So this is the equation used earlier. We can also use plus or minus sometimes. V1 plus or minus delta V by L1 minus delta L. This is the formula. But here we are not using similar type of equation, because in this particular case delta L value is going to become 0. Delta V equal to 0. When delta value V is 0, there is no change in volume. When there is no change in volume, divide everything divided by L. Divide everything by L. So that means V1 by L is nothing but A1. So you can look at V1 by L is nothing but A1, and L1 by L1 is nothing but 1 minus delta L divided by L1. So this is how the problem now. This is how the area of the failure in case of unconfined compression test. So that means this equation is also derived from the previous one, in which the delta value is equal to 0. The same formula you can look at here. A1 by 1 minus delta L by L. So accordingly, P axial load, A1 initial area of failure. So you can find out the area of failure and also sigma 1. Once sigma 1 is known, this plastic equilibrium equation is valid. Because here also the soil may be having only cohesive soil, cohesion C5 soil also. When soil is to be tested C5, properties of C5, we can use sigma 1 equal to sigma 3 tan square alpha plus 2C tan alpha. In this particular case, you know sigma 2 minor principal stress, sigma 3 intermediate principal stress, both are 0, no lateral pressure is applied. So the first term vanishes. So sigma 1 equal to only 2C tan alpha. You can look at 2C tan alpha. Normally we use U. Why it is U? Undrained. There is no drainage in this test. So that's why we are using Cu tan alpha. And it is 2Cu. Tan alpha means 45 plus 5 by 2. And here, if it is perfectly clay, phi value equal to 0. When phi equal to 0, it is 2Cu tan 45 plus 0, tan 45 equal to 1. So sigma 1 is equal to 2Cu, and Cu is equal to sigma 1 by 2, and Cu equal to Qu by 2. So in place of sigma 1, we are going to write Qu. Qu means unconfined compressive strength. Unconfined compressive strength during undrained condition. Similarly, from this you will get Cu undrained cohesion. So in this particular example, testing of unconfined compression test, if the unconfined compressive strength QU is known, you can find out the untrained cohesion Cu equal to Qu by 2. So this is how this particular experiment is very simple when compared to the triaxial test. And of course, in case of pure clay, Moore circle for unconfined compression test. When the soil is pure clay, then the failure plane is horizontal, and the minor principal stress sigma 3 equal to 0, and major principal stress here is sigma 1. Major principal stress here is sigma 1. And this is the only test where this Moore circle is passing through the origin. In all other cases, it is not passing through the origin. This is the only test where sigma 3 will be exactly equal to 0. And normally this cannot be conducted for the fissured clays. Already if the clay is containing some cracks, that soil cannot be tested in this, because once the cracks formed, and naturally after the application of the load, the soil is going to fail at that level, and whenever the soil is having some cracks, that is not allowed to be tested in this particular experiment. But here, in the examination point of view, we try to understand sigma 1 is P by AF, and AF is this equation, and straight away Cu equal to Qu by 2. That's all. And this remaining thing is background theory for derivation of the final equation. Then Wayne shear test. This Wayne shear test can be conducted both in the laboratory and also in the field. In the laboratory, the test size is very small, and field it is big, and it is particularly useful for the soft clays. Sometimes the question may be which of the following test is used or best suited for computing the parameters for the soft clays. So in such a case, the best answer is Wayne shear test is the correct method for finding the parameters of the soft clay. And it can be conducted in the field or laboratory. You can look at here. This shear test is having vanes. You can look at vane 1 and another vane, like that, where 4 vanes are provided on the perpendicular in a direction. And this vane is having overall diameter is D, or we can call it as vane width D, and the height of the vane is H. Height of the vane is H, and what is going to happen is a torque is applied at the top. So that the soil gets removed from it. By means of the application of the torque. So depending upon the magnitude of the torque, the shear parameters will vary. And here it is given T torque applied pi d square into C. Pi d means D is the diameter of the vane. You can look at here, either you can write capital D or small d. Pi d square into cohesion H by 2 D by 6. So this is the formula you need to remember, because there is no derivation for this. You have to remember. And this is the equation when both ends part take shearing. So that means the removal of the soil from both at the bottom and also from the top, then it is D by 6. When both the end part take shearing. And sometimes only at the bottom part taking shearing. So entire shear action is only at the bottom, then it will be D by 12. So a small change is there in the formula. Remember this equation and substitute the values for unknown parameter cohesion C. So C is the undrained cohesion, not trained, undrained, D-R-A-I-N-E-D, undrained cohesion. D overall diameter of the vane, height of the vane. And normally, as per IS, height will be normally equal to 2 times of the diameter. So in this particular exam test, you need to understand it is used for only soft clays. It is only for the soft clays. And remember this formula for computing the cohesion. Next, critical void ratio. Critical void ratio. So in sand, what is going to happen is sometimes initially dense sand, this curve, and sometimes initially loose sand. And when the initially it is having some void ratio, for dense sand void ratio is less, for loose sand void ratio will be more, and when you apply shearing force, it gets strained, and the plot is drawn between void ratio and also shearing strain. As the shearing strain applied on the dense sand, it gets loosened and void ratio increases and it reaches to the constant value. It reaches to the constant value. At the same time, when initially loose sand is subjected to shearing strain, the void ratio decreasing continuously and it is reaching to the constant value. That constant value is called the critical void ratio. Critical void ratio. And any amount of shear strain beyond critical void ratio, there is no change in critical void ratio. So that means by the application of the shearing strain onto the sand, whether the sand is in a loose state or in a dry state, it reaches ultimately a constant void ratio, which is called critical void ratio. Which is called critical void ratio. Then shear characteristics of cohesion-less soils. So cohesion-less soil means it is a loose sand. Loose sand. And you know that loose sand normally bulges if there is a small amount of water, and when it is completely submerged, it is in dry. When it is completely submerged in a state, it is having maximum density. Okay. Normally, the sands will fail by means of brittle failure in general. In case of dense sand, specimen shows clear failure plane, and this failure is called the brittle failure. So already I have seen several failures. Normally, the brittle failure means the small deformation occurs before failure of the specimen, and that is more in case of cohesion-less soils, whereas plastic failure is more in case of the cohesive soils. And several factors affecting the shear strength of the cohesion-less soils. For sandy soils, various factors that are affecting shape of the particle. If the shape of the particle, already I told you, and the angular particle will always gives more shear strength than the rounded particles. Similarly, gradation, soil, well-graded soil is always gives more shearing resistance, and similarly density, more dense soil is greater strength. Confining pressure, when the confining pressure is more, shear strength is more. And loading, normally it is independent of the loading, whatever may be the load, the factors shear strength does not affect. And type of minerals, what type of minerals it present, because void ratio is completely depends on the type of minerals present in it. Then capillarity, moisture, how much capacity it is going to absorb the water, etc. And some other factors affecting the shear strength of cohesive soils. Cohesive soils. So in cohesive soil, how much is the clay content? What are the drainage conditions? What is the confining pressure and plasticity index values? stress history disturbance. Stress history means how long the loads are acting on it, whether it is over consolidated, normally consolidated, or under consolidated, etc. So these are the various factors that affects the shear strength of the cohesive soils. So in general, the friction angle varies with the particle size, and the approximate relation you can look at here. The approximate relation you can see. Angle of internal friction phi dash equal to 36 plus phi 1, phi 2, phi 3, phi 4. That means in general for sands, cohesionless soil. That means for perfect cohesionless soil in all the directions, it is exactly 36 degrees centigrade, 36 degrees. But it varies. This can be decreased or it can be increased depending upon the numerical values of parameter 1, parameter 2, 3 and 4. Now let us see what are the various parameters. Phi dash equal to 36 represents an average conditions of the cohesionless soil, and phi 1 is it is because of the grain shape. This factor influences the shape of the grain, and for angular grains it will be 1, that means 36 plus 1, 37, and subangular 0, 36 plus 0, 0, and for rounded it is minus 3, that means 36 minus 3. For well rounded it is 36 minus 6, 38. Like that, it is influencing the shape of the grain. And second one is influence of grain size. Grain size, whether it is a sand, fine material or medium, accordingly 0, 1 degree, 2 degree. Correction factor for gradation. When the soil is poorly graded, minus 3. When the soil is medium graded, 0. When the soil is rounded, plus 3. Because for well graded soil, the shear strength increases. Similarly, other parameter, correction factor for relative density. So already you know that for more dense soil, shear strength will be more. For loose packing of the soil, shear strength is less. So accordingly it varies, minus 6 and also 6. So finally, the angle of the internal friction for a cohesionless soil can be computed 36 plus several other parameters. And finally, angle of internal friction for poorly graded soil is always less than angle of internal friction for the well graded soil. Then pore pressure parameters. Already you have seen this type of parameters are required in case of consolidation of the soils and also in the triaxial test setup. You know, sigma bar means effective stress equal to total stress minus pore water stress. Or otherwise you can also write delta U. Delta U means change in the water. So here delta U can be written as B into delta sigma 3. That means delta sigma 3 means change in deviator, change in cell pressure. Delta sigma 3 means cell pressure. Delta sigma 3 means change in cell pressure. And A multiplied by delta sigma 1 minus sigma 3. Already you know sigma 1 minus sigma 3 is called the deviator stress. Deviator stress. So this difference is called the change of the deviator stress. Change of the deviator stress. Whereas A and B here are the pore pressure parameters. A and B are the pore pressure parameters. So delta U can be written as delta U1 and delta U2. Delta U1 is the first term, D into delta sigma 3. That means B multiplied by change in cell pressure. And other term is B into A into change in deviator stress. So that is delta U1, delta U2. You know the meaning. Delta U1 is change in pore pressure because it is U. U means pore pressure. Change in pore pressure due to an increase in cell pressure. Delta U2 means, you can look at here, change in pore pressure due to an increase in deviator stress. So just try to remember this equation delta U equal to B into delta sigma 3 plus A into this. This equation is more important if there is any numerical question on pore pressure parameters. And here B is going to vary with several parameters 1 by 1 plus n into Cw by Cv. So here Cw and Cv are the coefficient compressibility of the properties. So Cw means it is for the pore fluid. You can look at Cw, compressibility of pore fluid. Cv means compressibility of the soil, and N is porosity of the soil. So the pore pressure parameter B depends on the porosity of the soil and compressibility of the fluid, compressibility of the soil. So when the soil is in dry condition, there is no pore fluid. There is no pore fluid. That means Cw value is much less than Cv. When Cw is much less than Cv, or otherwise Cw is zero, this term vanishes and B value equal to 1. So pore pressure parameter B equal to 1. When the soil is completely saturated, Cw is more dominating value than the soil, and this range will be equal to infinite, and finally B equal to 0. So that means pore pressure parameter B varies from 0 to 1. It's an important valid point. And again A equal to delta U by sigma 1 minus sigma 3. A value can be less than 0, more than 0, or any value above 1. There is no limit for it. It can be negative value, it can be positive value, it can be more than 0, more than 1, or less than 1. And B always varies with 0 to 1. So these are the, this is the entire theory. Particularly here, A and B are not the constants. A and B are not always constants, but B varies from 0 to 1. A can take any value, but B values depends on the UU test, whereas A depends on the CU test. So with this, the general theory regarding shear strength is over. And here, if you look at overall, very few formulas are involved in this. One is tau is equal to C plus sigma tan phi. Tau is equal to C plus sigma tan phi. Another equation is sigma 1 equal to sigma 3 tan phi plus 2c tan phi. 2c sigma 1 equal to sigma 3 tan phi plus 2c tan alpha. Sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha. That is another formula. One more formula is, in case of triaxial test, area at the failure AF will be equal to V1 plus or minus delta V by L1 minus delta L. And the same thing in case of unconfined compression test, Cu equal to Qu by 2. And in case of vane shear test, T equal to torque equal to pi d square multiplied by C into H by 2 plus D by 6. D by 6 is for both top and bottom shearing takes place. Whereas only bottom edge shearing takes place, then in place of D by 6 it is D by 12. Only these are the formulas to be remembered in case of shear strength of soils. So let us have a look for few problems in the shear strength of the soil. So you can see that these are the general problems, not to gate. Only after discussion of few problems, then we will move to the gate problems. The following results were obtained from direct shear test on cohesive soil sample. So these are the shear test stress results, normal stress and also shear stress at failure. The angle of internal friction and cohesion of the soil sample respectively are. So these values are given. What is the angle of internal friction and also what is the cohesion? So that is the question to be answered here. So here you can look at sigma 3. You know this formula sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha. Okay. In this particular first case, in the first case, what you have to do, you need to calculate the value of, I'll calculate this. In the first case, you have to calculate what is the value of the phi and what is the value of the c, or what is phi and also what is c. So what is the general equation that you know? In the case of shear stress, you know, tau is equal to C plus sigma tan phi. Tau is equal to C plus sigma tan phi. So here what are the values that you know? There are two combined values. Two combined values are known. The first one is shear stress 110. Shear stress 110 will be equal to C is not known plus sigma. What is corresponding sigma? 160 plus 160 multiplied by tan phi. So this is equation 1. And what is another equation? Tau is 130 will be equal to C plus what is corresponding normal stress? 240 multiplied by tan phi. This is second equation. By solving these two equations, you will get C equal to 70 and phi is equal to 14.03 degrees. That's all about the first question. So what is here? Normal stress means it is sigma. Shear stress means tau. The relation between these two holds tau equal to C plus sigma tan phi. Substitute these combination values in the equation. You will get two equations. The number of unknown parameters also 2 and solve these two. You will get phi equal to 14 and C equal to 70. That's all about the first question. If a triaxial test is carried out on the same soil sample with a cell pressure of 150 kilonewton per meter square, the deviated stress is. So the same values are represented in case of triaxial test. So in the triaxial test, cell pressure sigma 3 is given as 150 kilonewton per square meter. The question is what is deviated stress? Deviated stress is sigma 1 minus sigma 3. So here sigma 3 is known. You need to find out sigma 1. What is sigma 1 value? So for that, you know the alpha failure plane. Failure plane equal to 45 plus 5 by 2. Already phi value got 14.03. It is alpha equal to 52.01. In the case of triaxial test, and everybody knows that this is the associated equation. Sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha. All parameters are known, so you can find out sigma 1. Once sigma 1 is known, sigma deviator will be equal to, this is sigma d. Sigma deviator equal to sigma 1 minus sigma 3, so that you will get 275 kilonewton per meter. This is the first question. The second question, the test results of triaxial, 1 minute. The test results of triaxial compression test conducted under Undrained conditions on soil sample are as follows. Diameter of the sample 840, height of the sample 80, cell pressure sigma 3 100, increase in volume at failure 1.2 ml, axial compression 5 mm, deviator stress and total stress of the sample respectively or so you have to calculate here what is deviator stress and what is total stress of the sample. So for this what you do, sigma d equal to p by area failure, and all these are the parameters given, and change in volume delta v is 1.2 ml. 1.2 ml means 1.2 centimeter cubed. In terms of millimeter cubed, multiplied by 10 power 3 millimeter cubed. And 5 mm is given axial compression. Axial compression means delta L value. Delta L. You can look at volume. Initial volume is pi d square by 4 into height. Height. Then area of the failure is V plus delta V by L minus delta L. Substitute here, you will get area at the failure. Once area at the failure is known, deviator stress is P by AF, and you will get sigma D 442. And what is the total stress? Sigma 1 is nothing but sigma D plus sigma 3. So you will get 542. So what you are doing here, you first find out the area of the sample at the time of failure, and deviator stress will be equal to load applied divided by area of the sample at the failure, and accordingly you can find out deviator stress and also the total stress. Next one, an unconfined compression test. Remember unconfined compression. Unconfined compression test means it's very simple test that you can look. Cylindrical specimen of saturated soil fails at an axial stress of 160. So what is axial stress equation? Axial stress means QU. QU is nothing but 160 kilonewton per square meter. The failure plane makes an angle of 50. What is failure plane? Alpha. Alpha is equal to 50. Alpha equal to 54 degrees. In the problem it is given 54. Make a correction here 54. With the horizontal. The shear parameters are. So what is the here in this particular problem, what are the things that are given? The things that are given will be alpha equal to 45 plus 5 by 2. So in this alpha value is given as 54. So 54 will be equal to 45 plus 5 by 2. So from this get the value of 5. What is the value of the 5? It is not 54, it is 50. Okay, you take here it is 50. So 50. So 50 equal to 45 plus 5 by 2. From this you will get 10 degrees. Value of the 5 is equal to 10 degrees. And what is another question? Shear parameters are. What is the coefficient? What is the coefficient? Or what is the coefficient value? You know the equation QU equal to 2CU into tan alpha. QU equal to 2CU into tan alpha. QU 160, 2CU into tan alpha means tan 50 degrees. So CU equal to 58.12. Here remember that here in this particular case, phi value is not equal to 0. If phi value is not equal to 0, you have to use this equation relation. Already you know that sigma 1 equal to sigma 3 tan square alpha. But here phi is not 0. Failure plane is given 50. Accordingly, phi will be equal to 10 degrees. Phi will be equal to 10 degrees. So you have to use this formula sigma 1 equal to 2c tan alpha for computing both the shear parameters. It's also similar problem. It can be known. You can also see this. Okay. Now let us see another problem. An unconfined compressive strength of soil was found to be 80 kilonewton per square meter. So unconfined compressive strength means it is QU. You can look at QU is 80 kilonewton per square meter. A soil sample of same soil failed at a deviator stress of 180 kilonewton per square meter. Sigma D, deviator stress 180. And at a cell pressure of 90 kilonewton per square meter in triaxial test. See, first value is in the unconfined test. Second value and third value both are in the triaxial test because it is deviator stress and sigma 3 is the cell pressure. So these values will be obtained from the triaxial test for the same type of soil. So in the case of unconfined test, what is CU? CU is nothing but QU by 2. It is 80 by 2, 40. 80 by 2, 40. Then this is regarding the unconfined compressive strength test. Whereas for the triaxial test, between relation between sigma 1 and 3, sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha. So from this, what is sigma? Sigma 1 is sigma 3 plus sigma d. Sigma 3 is 90, sigma d 180. So sigma 1 is 90 plus 180, 270. So substitute this 270 here. 270 equal to sigma 1 equal to 270. Sigma 3 already known 90. Tan alpha not known. And 2c. Here c is computed from the unconfined compressive strength, which is 40. So that 40 is substituting here and tan alpha. So in the entire equation, the unknown value is tan alpha, and find out the tan alpha, alpha equal to 53.26 degrees. Once alpha is known, alpha is same as 45 plus 5 by 2. Accordingly, find out the phi value. So here a soil is tested with the both experiments. One sample is with the unconfined compression test. Another sample is tested with the triaxial test. So we are using both the equations for computing the position and also angle of internal friction. Okay, this is the last question that I will see for the non-gate questions. In a triaxial test, a soil specimen was consolidated under a cell pressure of 600. Cell pressure means sigma 3. You can look at sigma 3, 600 kilonewton per square meter. And the increased pore pressure reading was 420. Increased value means delta U1, 420. Axial load was then increased to give a deviator stress sigma d. That is delta sigma d is 550 and pore pressure reading 640. That means delta U2 640. So originally because of the deviator, because of the cell pressure, this is the pore pressure delta U1. Now because of the deviator stress, the pore pressure is delta U2. The pore pressure parameters A and B are respectively. What is A and what is B? So you know that equation delta U equal to B into delta sigma 3 plus A into delta sigma 1 minus delta sigma 3. So that is delta U1, delta U2. And you know all these parameters. Only thing you need to substitute here. So what is you have to substitute? You know delta U1 is B into delta sigma 3. So delta U1 420, delta sigma 3 600. Accordingly, B you will get. And delta U2 equal to B into A into this. It is called the deviator stress. Sigma 1 minus sigma 3 is called the deviator stress. That is given 550. And delta U2 640, you will get A. So ultimately only one equation is to be remembered. If you remember this equation, knowing delta U1 and also delta U2, corresponding values of delta sigma 3 and delta sigma d, you can find out the pore pressure parameters. So let's go to gate questions, previous examination questions. So look at here, it is a very recent question for gate in 2020, and look at 2020. In a in a drained triaxial compression test, a sample of sand fails at a deviator stress of 150. So it is given, deviator stress is given 150. Under a confining pressure of 50. What is confining pressure? Sigma 3. The angle of internal friction of the soil sample is. What is the test? It is a drained triaxial compression test, a sample of sand. Remember here, a sample of sand. Sample of sand means cohesion equal to 0. Sample of sand, C equal to 0. And the question is, what is C value? And it is conducted in case of triaxial test. Triaxial test means you know that formula, sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha. This formula you know. Or otherwise you can write the same equation in terms of n phi also. So once you know this, since it is given in the problem, it is sand and C value 0, so second term vanishes. Only the first term will exist. What is sigma 1 value? Sigma 1 means sigma 3 plus sigma d, because it is major principal stress. Sigma 1 is 150, sigma 3 is 50, sigma deviator 150, so that it will be 200. So what you do? Sigma 1 is 200 equal to sigma 3 is 50 multiplied by tan square. What is alpha? Alpha is nothing but 45 plus 5 by 2. Tan square 45 this. So in this equation, the unknown value is only 5. Get the value of 5. That will be the answer for it. You can see how simple the question is. This is the triaxial test equation. And in the triaxial test equation, it is clearly given that sample is sand. So C value is 0 and this term vanishes. And sigma 1 equal to sigma 3 tan square alpha. Sigma 1 is known, sigma 3 is known. Tan square alpha means 45 plus 5 by 2. Accordingly, get the value of 5. This is a very recent question in the examination. Or otherwise, already you know that the formula derived in some place, phi value will be equal to, phi value sin phi is equal to sigma 1 minus sigma 3 by sigma 1 plus sigma 3. Already you have seen this equation in theory, and substitute all the values and get the phi value. So either way you can do. Only thing is understanding the concept of the problem is more important for getting the solution. It's a big question that appears in 2019. So don't worry about the big question. When the question is big, only major problem is understanding the question. I'll read the question here. A 3 meter by 3 meter square precast reinforced concrete segments. You can look at. All these are the precast 3 meter by 3 meter blocks. Segments to be installed by pushing them through an existing railway embankment for making an underpass as shown in figure. So here what is going to happen? It is a railway embankment, and here underpass is to be provided. For that a push is required. Push is required, that is arranged by means of the jacks. A reaction arrangement using precast PCC blocks placed on the ground is made by the jacks. So far nothing is there. It's only explaining the arrangement of how the forces are acting on it. At each stage, the jacks are required to apply a force of 1875 kilonewtons. So that means through this jack, the horizontal force will be 1875 kilonewtons to push the segment. So here force applied is 1875. So when you apply 1875 here, what is the counter force on the precast blocks? It is also 1875 kilonewtons. Jacks will react against rigid steel plate placed against the reaction arrangement. So you can see at this place reaction will be developed, and for that vertical plate is provided and entire reaction is passing through that vertical plate. The footprint area of the reaction arrangement on the natural ground is 37.5 square meter. Footprint of the area of the reaction arrangement. You know that this is the reaction arrangement. For this reaction arrangement, at the bottom, the total area is 37.5 square meter. Unit weight of PCC block 24 kilonewton per meter cube. So this entire weight, density will be 24 kilonewton per meter cube. The properties of the natural ground are, natural ground means below this precast blocks is a C17, 525, gamma 18. Assuming that the reaction arrangement has rough surface. So this reaction arrangement is having rough surface at the ground and has the same property as that of soil. The factor of safety against shear failure is. So what is going to happen here is, it is some embankment and a push is required for underpass. For that reaction, some reaction arrangement will be provided by providing precast blocks, and entire reaction through the jacks is taken by the steel plate provided here. So here, what is the factor of safety with respect to the shear? So question, understanding the question is important. In the next page, you can look at here. This is the steel plate provided, and in this there is a push of 1875 kilonewtons. Already I told you, it is given in the problem. And reaction arrangement of precast RCC blocks. All these blocks are acting in the vertical direction. So vertical stress is sigma. And here foot area is 37.5 square meter. That means the total load is transmitting to the soil for an area of 37.5 square meter. And height of the blocks is 7.5 meter. And here, since the reaction is towards right, bottom shear stress is developed towards right, opposite in direction, which is tau. So this is the final concluding forces acting on the soil. So now, what is the factor of safety with respect to the bottom shear strength? So what you do? Already factor of safety is nothing but shear strength of the soil. Shear strength divided by tau, shear strength of the soil by tau value. C plus sigma tan phi by tau. And what is the sigma here? The sigma means the total weight divided by area. Area is 37.5. So what you do? Sigma equal to W by area. What is W? Volume into density by area. Volume is nothing but area into height. And area gets cancelled. You will get height into density. Height is 7.5 meter, density 24, 180 kilonewton per square meter. So that means sigma value is now 180 kilonewton per square meter. And what is S? You can look at S is nothing but the shear strength of the soil. What is the shear strength? C plus sigma tan phi. C plus sigma tan phi. Already C given. Sigma is just now known. For 25 also given shear property. So this is the shear strength of the soil. But shear strength of soil. But what is the shear stress developed at the bottom? Shear stress developed at the bottom is uh, tau is equal to jerk force by area. So what is the jerk force? Horizontal force is 1875. This horizontal force 1875 is acting over an area of 37.5. Over an area of 37.5. So tau is 50. So this is the stress developed because of the jacking action. Stress developed in the soil because of the jacking action. Whereas what is the shear strength of the soil? 100.94. What is the factor of safety? Shear strength divided by shear stress developed in the soil, which is 2.02. So here the question is, understanding the question is more important. Once you understood this, the solution is very simple. So next one, it also looks like big, but is the question is not of that much big. Okay, the total horizontal and vertical stresses at a point in a saturated sandy mediums are 170 kPa and to 300 kPa respectively. What are the question? Total horizontal and vertical stresses. So remember here it is saturated sandy soil. And sigma 3 170, sigma 1 300 given. The static pore water pressure is 30 kPa. Pore water pressure means 30 U. Symbol is U 30 kPa. At failure, the excess pore water pressure is measured 94.5. So this is called the excess pore water pressure U1 94.5. And shear stress on the vertical and horizontal planes passing through the point or 0. The effective cohesion is 0 because already in the problem it is given a sandy medium. So cohesion also 0, that is given. What is the question? The effective angle of internal friction is phi. The shear strength at the point is so at that point, what is the shear strength? You know, shear strength will be equal to the shear strength will be equal to S is equal to C plus sigma tan alpha. That is the C plus sigma tan phi. This is the formula that you know. You can also look here. Tau is equal to C plus sigma tan phi. This is the formula, final formula you need to compute. So here C value already given 0. So only find out sigma value and also phi value. Phi value is also given in the problem 36. So find out the sigma. So once you know the sigma value, you can substitute in this formula, you will get final equation. So how to calculate sigma 1 in the problem? How to calculate in the sigma 1 in the problem? You know that pore water pressure and also the horizontal vertical stresses are given. Find out the effective stresses in major direction and also minor principal stress direction. So sigma 1 bar is sigma 1 minus pore water, again minus pore water, because pore water at the beginning, pore water pressure at the beginning, and again excess pore water at the end. So that find out effective stresses sigma 1 bar and sigma 3 bar by deducting those two. So you will get what is sigma 1 bar, what is sigma 3 bar. And in the next, what you do is, find out the normal stress. What is the normal stress that is acting on it? Already you know this equation you have seen in the strength of materials principal stresses. Sigma normal equal to sigma 1 by plus sigma 3 by 2, sigma 1 minus sigma 3 by 2 into cos 2 alpha. Substitute the various values, you will get sigma normal, and substitute that sigma normal here, you will get the shear strength of the soil. So it is again a question in 2018. I'll take another 10 minutes. It's another question in appears in 2018. Can look at a conventional drained triaxial compression test was conducted on a normally consolidated clay sample under an effective confining pressure of 200. So confining pressure sigma 3 200, and that too it is given effective. You can look at effective confining. Effective means it is bar, sigma 3 bar. The deviator stress at failures was found to be 400. So sigma D is 400. An identical specimen of the same clay sample is isotropically consolidated to a confining pressure of 200. It's another one. 200. Another confining pressure of 200 and subjected to standard undrained triaxial compression test. So what is going to happen here? In this particular case, again confined pressure is the same. Sigma 3 is the same originally. Now also it is same. If the deviator stress at the failure is 150. Deviator stress at failure is 150. So what you do is, initially 200 is the cell pressure, sigma D equal to 400. From this sigma D equal to sigma 1 minus sigma 3, you can find out sigma 1 value. You can find out sigma 1 value, which is 600. And for clay samples, you know, sigma 1 is sigma 3 tan square alpha plus 2c tan alpha. And for clay, when it is given clearly in the problem, when it is given it is clay, sigma 3 okay. Another one is for undrained triaxial test, sigma 3 is 200, sigma D 150. It's a second experiment. For this experiment, again what you do is find out sigma 1 value. Sigma 1 is 350. So this is the second experiment conducted on the triaxial test, and first test conducted in the triaxial test will be with 200 and also 400, so that sigma 1 is 600. Sigma 1 600 in the first test, sigma 1 is 350 in the second test. So now U be the pore pressure developed. So what is sigma 1 bar? Sigma 1 bar means 350 minus U. 350 minus U. Sigma 3 bar means 200 minus U. Because sigma 3 is 200. You can look at sigma 3 200. 200 minus U. Sigma 1 is 350 here. 350 minus U. And U sigma 1 equals sigma 3 tan square 45 plus 5 by 2. And in this find out the U value. So the only unknown parameter here is U, and get the value of U. What is the question here? The question is, if the deviator stress at failure is 150, the deviator stress failure is 150, the pore pressure developed is, so what is the pore pressure developed here? That will be sigma bar will be equal to 350 minus U, this minus U, etc. So in the origin, there are two different cases of the test. Here what is going to happen? First one is effective confining pressure. Effective means 200 and 400 are bar. You can look at it is bar and it is also bar, so that sigma 1, sigma 3 are bar, effective stresses. Whereas in the second sample, it's a second sample, it is not effective, it is only the total sigma 3 and also sigma D. So basing on that, sigma 1 and sigma 3 known. Now effective stresses are sigma will be equal to minus u minus u. Substitute these values in the equation and get the unknown uh, pore pressure in the soil. And of course, it's a theoretical question that you can look at. Following are the statements related to the stress path in a triaxial testing of soil. Triaxial testing of soil. What are the things? P. If the stress at a point lies on the origin. Okay, something missed here. I will rectify and send the material. Next one. In 2017, a consolidated undrained triaxial compression test is conducted on a normally consolidated clay at a confining pressure of 100. So, a triaxial test, confining pressure 100 means sigma 3. The deviator stress at failure sigma d equal to 80. You can look at sigma d 80. And the pore water pressure measured at failure 50 kPa. Pore water pressure symbol is U, 50 kPa. The effective angle of internal friction of the soil, what is phi dashed? The question is phi dashed. And for question is phi dashed. So from this data, you can find out sigma 1. Sigma 1 will be equal to sigma 3 plus sigma d 180. And already I told you in the previous problem, effective stress sigma 1 bar equal to so 180 minus 50. This 180 minus 50. This is called effective. And sigma 3 effective means already sigma 300 minus this 50, you will get 50. So that means by using 130 and 50, you will get the effective phi value. Effective phi value. So here in this problem, it is given that for normally consolidated clay, for normally consolidated clay, sigma 1 equal to sigma 3 tan square for 45 plus 5 by 2 and second term vanished. And here use effective stress values, but and accordingly whatever the value of phi you got, that is called the effective angle of friction. So here sigma, when sigma 1 and sigma 3 are the total stresses, then phi is the normal angle of friction. If the sigma 1 and sigma 3 are the effective stresses, then phi is called the effective angle of friction. And it is in 2016. Here it is also similar to the previous problem, exactly similar to the previous problem. So I'll again read this. A drained triaxial compression test on a saturated clay yielded the effective shear strength parameters as 50 kPa. So here it is given effective stress sigma dash is 50 kPa and phi 22 degrees. Phi missed here, it is 22 degrees. Consolidated undrained triaxial test on an identical sample of this clay at a cell pressure of 200 kPa. So sigma 3 is 200. And here remember consolidated undrained. So consolidation takes place but there is no drainage, undrained. Pore water pressure 150 at failure. So U equal to 150. The deviator stress is, the question is what is sigma D? You know that sigma 3 effective is sigma 3 minus U, but sigma 3 is nothing but 200, U is 150, 50. So in this particular case, you know sigma equal to sigma 3 tan square plus 2c tan alpha, and substitute the various parameters. If all the parameters are known, you will get sigma 1 dashed. Once sigma 1 is known, sigma 1 dashed will be sigma 1 dashed is known, you can find out sigma 1, and accordingly deviator stress will be sigma 1 minus sigma d. you will get 104. So it's a routine process of using the standard equation sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha. If you remember this formula for only the substitution, you will get the required final answer. And it's a theoretical one. In the consolidated undrained triaxial test on a saturated sample, the pore water pressure is 0. You can remember consolidated. Consolidated means at the beginning pore pressure exists. Undrained means at the end no pore pressure. So that means at the end of consolidation stage only. Pore pressure is 0. Pore pressure is 0 at the end. That is during the shearing. During the shearing. During the failure. So there are two stages for the testing of the specimen in triaxial test. One is during the consolidation process and another one is shearing process. Consolidation process will be the first and then this one. So second stage, there is no pore pressure. Pressure will be equal to 0. And of course, it is also a routine problem that you can look at later. So this is an unconsolidated, untrained triaxial test. It is observed that an increase in cell pressure from 150 to 250 leads to a pore pressure increase of 80 kPa. So what is going to happen? Increase in cell pressure from 150 to 250. What is delta sigma 3? Delta sigma 3 is 250 minus 150, 100. And it leads to pore pressure increase. Pore pressure increase means delta U. Pore pressure increase is delta U 80 kPa. It is further observed that an increase of 50 kPa deviator stress. Here increase of deviator stress means delta sigma D 50. Results in an increase of 25 kPa in pore pressure. So what is that? Delta U is now 25 kPa. The value of Skempton's pore pressure parameter B. You know that there are two parameters, Skempton parameters A and B, and it is the question for finding B. For finding B, already you know that delta U1 equal to, you know that already the equation delta U1 will be equal to B multiplied by delta sigma 3. This is the equation. So from that equation, directly you can find the value which is 0.8. So like that, all the questions are related to the GATE examination. You can look at the entire base concept. You can answer this particular question. And similarly, it's also a very simple question. Substituting, knowing the equation of tau equal to C plus sigma tan phi. And it is it is a question by simple substitution of various values in the equation. I will just go through once. A field is the question itself is very big, but answer is not so tough. A field vein shear testing instrument was inserted completely into a deposit of soft saturated silty clay with the vein rod vertical such that the top of the blades were 500 mm below the ground surface. Top of the blade is 500 below the ground surface. That means what is the value? H is given as 500 millimeters height of the blade. Upon the application of rapidly increasing torque about the vein rod, the soil was found to fail when the torque reached. So torque is given as 4.6 Newton meter. Assuming mobilization of undrained shear strength on all failure surfaces to be uniform and the resistance mobilized on the surface of the vein rod to be negligible, what would be the peak undrained shear strength of the soil? The question is CU. So all the lines that are given in the question are the generalized lines, and here overall is what are the various parameters given. Height is given, torque is given, what is CU, associated diagram also given. From the diagram, you can look at D will be equal to 50 millimeters. You can look at D equal to 50. So all the parameters are known. All the parameters means T is known, D is known, H is known, D also known, and using this substitute and get the value of the C. That's all about it. So question is big. It is also associated with the diagram, and no need of worry. Of course, here height is given as 100 millimeters. So depth below the surface is 500. Depth below the surface, this entire depth below the surface is 500. But height of the vein given is 100 millimeters, and use appropriately various values and obtain it. So with this, almost all problems covered with the previous discussion, and you can look at these are the very small problems when compared to the problems that are discussed just now. Because in all these, only one equation. If you just remember this equation, you will get entire solution for it. And similarly, in the other case, only this equation, similar type of problem it is. And this is also sensitivity, which is very simple. I'll deal it. The unconfined cohesion of a remolded clay 10. Already you know in the earlier chapter, sensitivity is nothing but QU by QU. QU of, what is QU of undisturbed sample, QU of undisturbed sample, and QE of remolded sample. So this is the sensitivity formula, already you have seen earlier. And in the problem it is given, if the sensitivity of the clay is 20, the corresponding remolded compressive strength is. So if you just know the value, if you just know the value, CU is given in the problem 10. Undrained cohesion. Undrained cohesion means CU is given. What is QU? QU by 2 is nothing but CU. So from this, QU is nothing but 2CU, it is 20. So you have to calculate in the reverse order. And sensitivity is also given. You can find out the remolded QU. So like that, simple problems. It's also very simple one. Of course, it is already discussed. Like that, several other problems are there. And all these problems are similar. You can also look at here. This formula is known. Then by substitution, you will get a very unknown parameter. So like that, several other questions with solutions also given here, and go through all these questions. Go through all these questions, and if you have any doubts, you can send mail to my personal mail created only for this purpose. Personal mail created only for this purpose, so that I can answer all your doubts in the class, or otherwise personally I can send the solution to the individual. So just you can note down the email given, bjrcivilgate @gmail.com, so that all the questions will be answered in the next class, or otherwise I can send the solutions to the respective individual candidates. So with this, shear strength of the soils is completed, and tomorrow I am going to take up the new chapters, stress distribution and also stability of slopes. So tomorrow I can finish both the chapters, stability of slopes and also stress distribution in the soils. So thank you very much.